Comes from if you are doing job hunting or other things like that, is you know someone who knows someone, things like that. Networks can be found in all walks of life. A city's public transportation system, the London Tube, is a great example of this because it is a very well interconnected network, and it's a very big one too. Infrastructure such as the national power grid for electricity, another very important network. Meeting and greeting your neighbors, again, more of a safety network in that case. The postal system for sending letters and parcels, and so on and so forth. You can see networks everywhere in your life, and they're very, very important concepts. But more specifically, in computing, networking is the same idea, just dispersed to technological devices. Take your phone as an example. The reason that you have it is to access things, because if it didn't do anything, it'd be kind of like an old, an old Palm Pilot or an old PDA, where, it's not that much good. It may be a calculator, disputing the claim that your teacher would say that you wouldn't have a calculator carried around in your pocket all the time. But you can see the importance of networks. We'll cover how these devices communicate with each other and the rules that follow. In computing, a network can be formed by anywhere from 2 devices to billions, so it doesn't really matter as long as it's more than, or 2 or more. These devices include everything from your laptop and phone to security cameras, traffic lights, and even farming. Networks are integrated into our everyday life, be it gathering data for the weather, delivering electricity to homes, or even determining who has the right way at a road. Right of way, rather. Because networks are so embedded in the modern day, networking is an essential concept to grasp in cybersecurity. Take the diagram below as an example. Alice, Bob, and Jim have formed their own network. We'll come onto this a bit later. We'll talk about this a little bit later on, so you can see just a basic network. Networks come in all shapes and sizes, which is something that we'll also come on to discuss throughout this module. Let's go ahead and dive into the question. What is the key term for devices that are connected together? That is a network. And there we go. We'll go ahead and close that. And let's go ahead and go into task 2. What is the internet? Now that we've learned what a network is and how one is defined in computing, just devices that are connected, let's explore the internet. The internet is one gigantic network that consists of many, many small networks within itself. Using our example from the previous task, let's now imagine that Alice made some new friends named Zane and Toby that she wants to introduce to Bob and Jim. This is starting to sound like an Office reference. The problem is that Alice is the only person who speaks the same language as Zane and Toby, so Alice will have to be the messenger. And you can see that Alice is here in the middle, where she's the messenger for these two. Because Alice can speak both languages, they can communicate to one another through Alice, forming a new network. The first iteration of the internet was within the ARPANET project in the late 1960s. This project was funded by the United States Department of Defense, or Defense Department, and was the first documented network in action. However, it wasn't until 1909 when the internet as we know it was invented by Tim Berners-Lee by the creation of the World Wide Web, or otherwise shortened to WWW. It wasn't until this point that the internet was used as a repository for storing and sharing information, like it is today. Let's relate Alice's network of friends to computing devices. The internet looks like a much larger version of this diagram, and you can see this is a very abbreviated, intensely abbreviated version of the internet, where we have many small networks that are interconnected with a translating device in the form of a router. Even though this is not necessarily translating, it's Nat and Pat. Don't worry about that right now. Just know that this is just a way that we have gateways for our private networks to talk to the internet. As previously stated, the internet is made up of many small networks all joined together. These small networks are called private networks. So think your home network, a business network, things like that. Where networks connecting these small networks are called public networks. Try saying that 10 times fast. Or the internet. So to recap, a network can be one of two types: a private network or a public network. Devices will use a set of labels to identify themselves on a network, which we will come onto in the task below. So who invented the World Wide Web? That will be Tim, I'm going to have to grab his name from up here, as I can't spell it. Tim Berners-Lee, and we can just copy that. And there we go. if I don't leave the other part of the answer on there. All right, perfect. Let's move into task 3, identifying devices on a network. To communicate and maintain order, devices must be both identifying and identifiable on a network. What use is it if you don't know whom you're talking to at the end of the day? If you're just yelling into the void and the void starts talking back, that's a little strange. Devices on a network are very similar to humans in the fact that we have two ways of being identified via our name and our fingerprints, among a couple other things, but those are good generalizations. And now we can change our name through deed poll, but however, we can't change our fingerprints. So we can change our name, we can't change our fingerprints. That's the general gist of this. Every human has an identical set or individual set of fingerprints, which means that even if they change their name, there is still an identity behind it. The general idea behind this is that, yes, you can change what you're called, and that's something that, you might have a nickname or other things like that, but you're always going to have some permanently identifiable marks. And computers have the same thing. Devices have the same thing. They have an IP address, which can change, but they have a what's in theory a globally unique MAC address or immediate access control address. You can see that right there. Think of it's kind of similar to a serial number, but these are all standardized. And it's split up in a couple different ways, where the first half is the manufacturer and the second part is the unique part. I won't go too far into this, but just know that while you can be called different things, your MAC address is generally, in theory, globally unique. IP addresses. Briefly, an IP address, or Internet Protocol address, can be used as a way of identifying a host on a network for a period of time, where that IP address can then be associated with another device without the IP address changing. First, let's split up precisely what an IP address is in the diagram below. So before we go into this, think of this as your street address. Other people can live there. You probably aren't the only person that's lived at that address, and you might not be the only person, using that computer at that address. And this can change hands, and it might change over time with, people changing the way that the address system is set up for streets, things like that. But this is how we know how to send mail to you. And the same thing goes for computers. An IP address is a set of numbers that are divided into 4 octets, and you can see one here, one here, one here, and then one here. And you can see that these have a range of 0 to 255. This is because they're made up of 8 binary bits, if I remember correctly, and the range for that is 0 with all of the bits being turned off, and then if you turn them all to ones or everything is on, your limit is 255. The value of each octet will summarize to be the IP address of the device on the network. So all of these put together, the individual octets can mean things, but generally speaking, don't worry about that right now. This is your street address on the network. It's how your computer knows to talk to someone else. So this might be your router's address on your home network. This actual network itself is pretty common for home networks. So 192.168.1. And this last bit would be what changes, or sometimes this is a 0, but these first two pretty common for home networks. And that's where you have the first and second octet, or octets that are static. I won't go too far into that, but just know that this might be a router address. It's very common for that. What's important to understand here is that the IP addresses can change from device to device, but they cannot be active simultaneously more than once. So if you have a street address, your neighbor can't have the same one. You can swap houses with your neighbor, and that'd be a little weird, but you will have a different address living at that house. You can't have that collision, because that causes problems, and both of the devices will say, hold on, we need to figure something out here. IP addresses follow a set of standards known as protocols. These protocols are the backbone of networking and force many devices to communicate in the same language, which is something that we'll come on to another time. However, we should recall that devices can be on both a private and public network. Depending on where they are will determine the type of IP address they have, a public or private IP address. So real quick, there was a note in here. Protocols. So the reason that we have that, and the reason that we all use the same language, metaphorically speaking, to talk to each other over the internet, is because when the internet first came out, we had a bunch of different protocols, and sort of like trying to talk to a bunch of different people that don't speak the same language doesn't really work out. You can kind of get the general gist, but The communication just doesn't happen. So we established these protocols, and they were something that were much more solidified with the creation of Wi-Fi. Definitely something that if you're interested in learning a little bit more, the Wikipedia page has a great summary of why this is important. But generally speaking, we have to have rules. Otherwise, a lot of device manufacturers like Microsoft and HP, IBM, you go on, name whatever one you want, they'll just make their own and claim it's the fastest. And the other devices won't work with it because they want you to buy their device. So just keep that in mind. That is why we have protocols that force everyone to use the same standardized communication. A public address is used to identify the device on the internet, whereas a private address is used to identify a device amongst other devices. Think of this home network versus anyone can talk to it on the internet, generally speaking. Take the table and screenshot below as an example. Just keep that in mind. That is why we have protocols that force everyone to use the same standardized communication. A public address is used to identify the device on the internet, whereas a private address is used to identify a device amongst other devices. Think of this home network versus anyone can talk to it on the internet, generally speaking. Take the table and screenshot below as an example. Here we have two devices on a private network, and we can see the private ranges right here. There are three private ranges predominantly. 192.168, and these last two bits can change, or last two octets rather can change, is a major one. The 10.0.0.0 is another big one, and there's another one that I can never remember the full of it because it has a range in the second octet. I recommend taking a look at these, and we might go over them later in the room, but just know that there are three very distinct ranges that the private IP ones can fall into, and these would be public because they don't fall into that range. And we can see them labeled over here on the side. These will be on the same network because these are, well, okay, in theory they could be on the same network. They might not necessarily, but they're very likely to be because we have 192.168.1 and then 74 and then 77. These could exist on the same network because they don't conflict, and they could talk to each other in theory if there's not routing rules or other restrictions in play. And here you can see this might be a screenshot from a router that we have these two devices with their MAC addresses. Don't worry too much about this right now. Just know that this is in theory unique. And these are the private IP addresses that they have on the network. And they were assigned via DHCP, which just means that I have a pool of addresses, first come, first serve, and we give them out. And they're not necessarily like, you get this one permanently on this network. That would be a static addressing. These two devices will be able to use their private IP addresses to communicate with each other. However, any data sent to the internet from either of these devices will be identified by the same public IP address. So your home would have a public IP address in this case, but you'll have your private IP, your private network sits behind that. Public IP addresses are given by your internet service provider, or ISP for short, at your monthly bill. So when you have an internet service contract set up, you'll have an IP address that is associated with your home. Sometimes this can be associated with a couple of different homes. This can get a little weird. You can pay to have this not change and be static, but just know that this is something that exists on the public internet in this case. As more and more devices become connected, it is becoming increasingly public internet. You can pay to have this not change and be static, but just know that this is something that exists on the public internet in this case. As more and more devices become connected, it is becoming increasingly harder to get a public address that isn't already in use. For example, Cisco, an industry giant in the world of networking, estimated that there will be approximately 50 billion devices connected on the internet by the end of the 2021, so the current year in the time of this recording. Enter IP address or address versions. So far, we've only discussed one version of the Internet Protocol addressing scheme known as IPv4. IPv4 is pretty old. It had some limitations, and we didn't really anticipate this many devices to be connected to the internet, but we have smart homes and other things like that, which dramatically increases the number of devices that we're connecting to the internet on the whole, especially if they need public addresses. And this uses a numbering system of 2 raised to the 32nd IP addresses, so 4.92 or 29 billion. So you can see why there's a shortage, because we have more devices that are connected to the public internet than we have available for IPv4 addresses. IPv6 is a, relatively new iteration of the Internet Protocol addressing scheme to help tackle this issue. Although it is seemingly more daunting, it boasts a few benefits. So it supports up to 2 to the 128th power of IP addresses, so this is 340 trillion plus. In theory, we should never run out of these. We'll see what happens, just because more devices are being connected. In theory, we should never run out of these. We'll see what happens, just because more devices are being connected. And it resolves that big issue with IPv4 because we were going to run out. Now we really can't. More efficient due to new methodology. So there's a bunch of new technologies that were introduced in this. Don't worry too much about knowing this. Just know that in general, IPv6 has a bunch of cool new shiny features. And you can see there's a comparison of those two addresses. So with an IPv4, we had these 4 octets, and this is a lot longer. I won't go too much into detail, just know that IPv6 exists. This is not as common to see on home networks. Generally speaking, you need to know about this, just that it exists. And once you get further into penetration testing or defense, knowing that IPv6 is another way that things can talk to each other, that's just another thing to be aware of. So that's all you need to know at this point in time. Just focus on IPv6, and this is going to be where most everybody focuses nowadays anyhow. Let's go ahead and talk about MAC addresses. Devices on a network will all have a physical network interface, which is a microchip board found on the device's motherboard. This is your Ethernet port, or your Wi-Fi card, whatever this is. This network interface is assigned a unique address at the factory it was built at, called a MAC address, a media access control address. This is referred to as burnt in quotation marks. This is because in theory it can't be changed. You can do spoofing and other things with this. Don't worry about that too much right now. Just know, again, this is in theory globally unique, and the odds that you're going to have two devices on the same network that have the same MAC, very, 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 very infinitesimally small chance. Big businesses can run into this every once in a while, but it's pretty rare. The MAC address is a 16-character hexadecimal number, a base 16 numbering system used in computing to represent numbers. You can see that this is hex base 16, where it rolls over from 9 and it starts small chance. Big businesses can run into this every once in a while, but it's pretty rare. The MAC address is a 16-character hexadecimal number, a base 16 numbering system used in computing to represent numbers. You can see that this is hex base 16, where it rolls over from 9 and it starts A, B, C, D, E, and then F is the last one. And you can see that the MAC address is a 16-character hexadecimal number, a base 16 numbering system used in computing to represent numbers. You can see that this is hex base 16, where it rolls over from 9 and it starts A, B, C, D, E, and then F is the last one. And you can see that this is an example of a MAC address here, where it is 6 groups of 2 of these. The first 6 characters represent the company that made it, so right here, that made the networking interface, and the last 6 is in theory a unique number. So, and you can see that broken apart down here. 9 to represent numbers. You can see that this is hex base 16, where it rolls over from 9 and it starts A, B, C, D, E, and then F is the last one. And you can see that this is an example of a MAC address here, where it is 6 groups of 2 of these. The first 6 characters represent the company that made it, so right here, that made the networking interface, and the last 6 is in theory a unique number. So, and you can see that broken apart down here. However, an interesting thing with MAC addresses is that they can be faked or spoofed, as I mentioned before. This spoofing occurs when a network device pretends to identify as another by using its MAC address. When this happens, it can often break poorly implemented security designs that assume devices talking on a network are trustworthy, because they're not. Don't worry too much about this. This is more of a situation of just know about this. It's not something too major, and you'll come across it later on in your security career. Take the following example. A firewall is configured to allow any communication going to and from the MAC address of the administrator. If the device were to pretend or spoof this MAC address, this firewall would now think that it is receiving communication from the administrator when it is not. So places such as cafes, coffee shops, and hotels alike often use MAC address control when using their guest or public Wi-Fi. This configuration could offer better services, i.e. a faster connection for a price if you're willing to pay the fee per device. The interactive lab attached to this task has been made to replicate this scenario. And let's go ahead and spin that up right now. So in theory, you could just pretend to be someone else. That is something that happens. Let's go ahead and scroll back down to the practical bit. The interactive labs simulate a hotel Wi-Fi network. You have to pay for the service. You'll notice that the router is not allowing Bob's traffic, Bob being right down here, but Alice's packets, green, right here, are going through just fine because she paid for the Wi-Fi. Try changing Bob's MAC address to the same as Alice's and see what happens. And let's see, I think I need to scroll down, and let's try changing these to be the same. If I can type this all out. Let's see if I can just highlight this. Copy. Oh, I can. And there we go. And now suddenly we can talk out to the internet. And we got a flag. Don't worry too much if you can't read that. I'm going to go ahead and paste that here. So THM, you got on Try Hack Me. So in theory, you could spoof your MAC address if you haven't paid for Wi-Fi like this. Just something to know about. Again, just know the idea that MAC address control exists and that MAC addresses are in theory globally unique. That's really all you need to get from this. Let's go ahead and go into the other questions. What does the term IP stand for? That is going to be Internet Protocol. What is each section of an IP address called? That is going to be an octet. How many sections in digits does an IP address have? That will be 4. And let's see, what does the term MAC stand for? Media address control, I believe. It should be access control, I'm guessing. There we go. Perfect. Let's go to move into task 4, ping with ICMP. Let's go ahead and pull this up so we don't have to watch packets fly across. Ping is one of the most fundamental network tools available to us. Ping uses ICMP, Internet Control Message Protocol, packets to determine the performance of a connection between devices. For example, if the connection exists or is reliable. So this is a way that we can determine performance. The time taken for ICMP packets traveling between devices is measured by ping, such as in the screenshot below, and we can see the output of a ping command here. This measuring is done using ICMP's echo packet, and then ICMP's echo reply from the target device. And you can see that we have a ping command with our target up here, and then we have our time here, and then it looks like we have determine performance. Ping is one of the most fundamental network tools available to us. Ping uses ICMP, Internet Control Message Protocol, packets to determine the performance of a connection between devices. For example, if the connection exists or is reliable. So this is a way that we can determine performance. The time taken for ICMP packets traveling between devices is measured by ping, such as in the screenshot below, and we can see the output of a ping command here. This measuring is done using ICMP's echo packet, and then ICMP's echo reply from the target device. And you can see that we have a ping command with our target up here, and then we have our time here, and then it looks like we have our average back here. So the average performance, or how much time it takes us to talk to another device. Pings can be performed against devices. So the average performance, or how much time it takes us to talk to another device. Pings can be performed against devices on a network, such as your home, or how much time it takes us to talk to another device. Pings can be performed against devices on a network, such as your home network or resources such as websites. This tool can be easily used and comes installed on operating systems, resources such as websites. This tool can be easily used and comes installed on operating systems, OSs, such as Linux and Windows. The syntax to do a simple ping is ping, and then the IP address right here, or your website URL. So ping is the command, and then either the website URL or the IP address. And you can see that demonstrated down here. Here we are pinging a device that has the private address of 192.168.1.254. Ping informs us that we have sent 6 ICMP packets, all of which were received with an average time of 5.3 seconds. Now you are going to do the same thing to ping the IP address of 8888. This is one of Google's DNS servers on the deployable website in this task. Pinging the correct address will reveal a flag and answer the following questions. Let's see. So let's go ahead and dive into the questions. What protocol does ping use? ICMP, if I can type. What is the syntax to ping all 10s? That will be 10 or ping 10, 10, 10, 10. And what flag do you get when you ping quad 8s? Let's see. I guess we just put it up here. And then we'll go ahead and send our ping request. And we'll give it just a moment to finish its ping. And there we have our flag. I pinged the server. Let's go ahead and copy that out, and we'll paste it in. And let's move into task 5. Continue your learning Intro to LAN. Continue your learning by joining the Intro to LAN room. We'll go ahead and mark that as complete, and otherwise I will see you in the video for that room. But until then, as always, I have the Try Hack Me Discord, as well as the subreddit linked in the video description below. If you have any questions, feel free to hop in there. But until next time, happy hacking! Linked in the video description below. If you have any questions, feel free to hop in there. But until next time, happy hacking! Hey everyone, welcome back to another video here on Try Hack Me. I'm John, and today we're going to be taking a look at the room Intro to LAN. Learn about some of the technologies and design. Hey everyone, welcome back to another video here on Try Hack Me. I'm John, and today we're going to be taking a look at the room Intro to LAN. Learn about some of the technologies and designs that power private networks. That being said, let's go ahead and dive right into task 1, introducing LAN topologies. Local area network, LAN topologies. We'll go ahead and click the view site. I think it's already loaded, but we'll just make sure. Over the years, there have been experimentation and implementation of various network designs. In reference to networking, when we refer to the term topology, we're actually referring to the design or look of the network at hand, so how everything's actually connected. Let's discuss the advantages and disadvantages of these topologies below. First, let's talk about the star topology. The main premise of a star topology is that devices are individually connected via a central networking device, such as a switch or a hub. This topology is the most common found today because of its reliability and scalability, despite the cost. Any information sent to the device in this topology is sent via the central device, which connects everything. Let's explore some of these advantages and disadvantages of the topology below. Because more cabling and the purchase of a dedicated networking equipment is required for this topology, it is more expensive than any of the other topologies, and we'll discuss a few more below. However, despite the added cost, this does provide some significant advantages. For example, this topology is much more scalable in nature, which means that it is very easy to add more devices as the demand for the network increases. Unfortunately, the more the network scales, the more maintenance is required to keep the network functional. This increased dependence on maintenance can also make troubleshooting faults much harder. As there's more places, there's more cables, there's more things to go wrong in general. Furthermore, the star topology is still prone to failure, albeit reduced. For example, if the centralized hardware that connects devices fails, these devices will no longer be able to send or receive data. Thankfully, these centralized hardware devices are often very robust. Switches, they don't die very often, and when they do, it's very obvious that they're dead, and it's pretty easy to replace them. They're usually not terribly expensive as well, as far as networking hardware goes. As you get ones with nicer features, they definitely go up in price, but for just a basic one for home use, they're like $25 or something like that, which on the scale of networking things, that's not too bad. But you can see in this how everything's connected via a central hub. Bus topology. This type of connection relies on a single connection, which is known as the backbone cable. This type of topology is similar to the leaf off a tree in the sense that the devices, or leaves, stem from where the branches are on the cable. Because all data destined for each device travels along the same cable, it is very quickly prone to becoming slow and bottlenecked if devices within the topology are simultaneously requesting data. This bottleneck also results in very difficult troubleshooting because it quickly becomes difficult to identify which device is experiencing issues with data all traveling along the same route. However, with this said, bus topologies are often one of the easier and more efficient topologies to set up because of their expense. And you can see that there's this big connecting thing that there's not a lot of cabling involved there because you just have one dedicated mega cable. Because of their expenses such as cabling or dedicated network equipment used to connect these services. So lastly, another disadvantage of the bus topology is that there is a little redundancy in place in case of failures. This disadvantage is because there is a single point of failure along the backbone cable. If this cable were to break, devices can no longer receive or transmit data along the bus. Let's talk about ring topology. The ring topology, also known as token topology, boasts some similarities. Devices such as computers are connected directly to each other to form a loop, meaning that there is little cabling required and less dependence on dedicated hardware such as networks or switches or things like that within the star topology. A ring topology works by sending data across the loop until it reaches the destined device. Using other devices along the loop, they'll forward the data, so essentially it just gets passed along these points. Interestingly, a device will only receive data from another device in this topology if it does not have any to send itself. If the device happens to have data to send, it will send its own data first before sending data from another device. Because there is only one direction for data to travel across this topology, often counterclockwise or clockwise, just one of the two, it is fairly easy to troubleshoot any faults that arise. So for example, if you had a break right here, and suddenly this device can't receive data from this device, well, fairly obvious that the cable's probably bad there. However, this is a double-edged sword because it isn't an efficient way of data traveling across a network, and it may have to visit multiple devices first before reaching the intended device. Lastly, ring topologies are less prone to bottleneck. Such as within a bus topology, as large amounts of traffic are not traveling across the network at any time. The design of this topology does, however, mean that a fault such as a cable cut or a broken device will result in the entire networking breaking or just failing altogether. One thing to note here, this is less common to see. This is something that you would probably see if you have a mesh network, that it might leverage a ring topology to pass things between those different nodes in the network. However, that's not exactly all that common. The one that you're likely to see in most cases is probably this star, just because it's very common, it's very easy, and often enough in your home network, this is probably what you're using anyways, where you have one router that has a Wi-Fi access point on it and everything connects to the same access point. So just be aware that this is probably the most Wi-Fi access point on it and everything connects to the same access point. So just be aware that this is probably the most important one, but you do need to know about these other topology types. Let's talk about what is a router. It's a router's job to connect networks and pass data between them. It does this by using routing, hence the name router. Routing is the label given to the process of data traveling across networks. So what do we mean when we say across networks? This means networks with different addressing schemes. So maybe I have a home network and you have a home network, but if I want to send something to you, maybe an email, that has to cross the public internet too. So we have our routers that sit on the edges of those networks. So where the internet comes into my house at what's called the demarc point, and then where it comes into your house at the demarc point there. And that does the translating. It handles how routes are created. And when I say routes, I mean general rules of how you can talk to devices across those networks. So it uses the destination as a means to break down where it needs to send things. Think of the old like turnstile where you'd see marbles going in and they would go out one specific end of maybe a marble contraption. It just routes things. And in this case, it'd be, instead of marbles, it would be packets. So uses routing rules to just control where it needs to send things. Routing is useful when devices are connected by many paths, such as in the example diagram below. So you can see that maybe this is the internet here in the middle, where we have my house and then your house here, and I'm going to send you an email, but it needs to go between those other networks, or maybe just different parts of a building. But you can see that these handle the translation so that this network can be its own thing, and this network can be its own thing as well. Let's talk about switches. Switches are dedicated devices within a network that are designed to aggregate multiple other devices, such as computers, printers, and or other networking capable devices using internet, or ethernet rather, so the actual cable. These various devices plug into a switch's port. Switches are usually found in larger networks such as businesses, schools, or other similar sized networks, where there are many devices to connect to the network. Switches can connect a large number of devices by having ports, groups of ports, 4, 8, 16, 24, 32, and 64 devices to actually plug into, and they can get even bigger than that. So generally speaking, they're going to come in this multiple of 4. Here, it's just because it's easier to make them and it's easier to address devices in that way. So these will not necessarily have routes such as routers do, but they have a way of actually identifying which device is plugged into that cable, and from there it can kind of form a routing table internally where it knows how to send these packets along. So unlike routers, these devices do not perform routing, as I just mentioned, in the sense of directing paths along a certain route using IP protocol. Instead, switches use a technology called packet switching to break down pieces of data into smaller, more manageable chunks of data called packets. This technology allows for the efficiency of a network, or because large pieces of data take up more resources. If you want to send a large chunk, like maybe a large part of a game download at once, that's not very efficient. That's a lot of data traveling, and if you have to keep it all connected, that is potentially just going to take up the entire network, its processing. However, it's much, much easier to transmit that in small little bite-sized pieces. It's sort of the same concept as carrying up furniture, or if you need to, it's easier to break it down and carry light boxes rather than one really big item, as it takes everything or all of your resources at that point. And you can see again how it mentions the efficiency there. So both switches and routers can be connected together. The ability to do this increases the redundancy or the reliability of a network by adding multiple paths for the data to take. If one path goes down, another can be used. Whilst this may reduce the overall performance of a network because packets have to take longer to travel, there is no downtime. A small price to pay considering the alternative. So quick practical. Attached to this task is an interactive practical featuring the discussed LAN topologies, learning about the various ways in which they are vulnerable to breaking. Break the LAN topologies to retrieve the flag. So the first question here that we have is, what does LAN stand for? That is going to be local area network. What is the verb given to the job that routers perform? That should be routing. There we go. What technology do switches use to break down large pieces of data into smaller, more manageable packets? That is going to be packet switching. What topology is cost efficient to set up? Let's see. I'm guessing this is the bus topology. And there we go. What topology is expensive to set up and maintain? So that is going to be the star because you have more networking cables and things like that. And then let's go ahead and complete the interactive lab. Topology flaws. This lab will take you through the flaws in different network topologies. First, we have the ring topology. In ring, you can see packets of data. Bus topology. With the bus topology, all devices are connected to a single cable, often called the backbone. Data is sent in both left and right directions down the backbone until the packet's destination. As we've previously discussed throughout the module so far, networks can be found in all shapes and sizes, ranging from small to large. Subnetting is the term given to splitting up a network into smaller, miniature networks within itself. Think of it as slicing up a cake for your friends. There's only a certain amount of cake to go around, but everybody wants a piece. Subnetting is how you decide who gets what slice and reserving such a slice of this metaphorical cake. Take a business, for example. You will have different departments such as accounting, finance, and human resources. You need to somehow split up your network between these different departments, though. And here we can see we have a diagram demonstrating exactly that, where we have the internet with a router on the edge and then a switch connecting everything in a star topology. And then we can see this is further broken up where we have our individual sections, which is where subnetting comes in. Once you know where to send information in real life to connect or to the correct department, networks need to know this as well. Network administrators use subnetting to categorize and assign specific parts of a network to reflect this. Subnetting is achieved by splitting up the number of hosts that can fit within the network, represented by a number called a subnet mask. Let's refer back to our diagram on the first room in this module. And here we can see that we have our IPv4 address with the 02255 octets. As we recall, an IP address is made up of 4 sections called octets. The same goes for a subnet mask, which is also represented by a number of 8 bytes, 32 bits, ranging from 0 to 255. Subnets use IP addresses in 3 different ways: to identify the network address, to identify the host address, and identify the default gateway. Let's talk about what these actually mean. Let's split these 3 up to understand their purposes in the table below. So first off, we have the network address. This is a bit of a confusing topic, but know that this is a very simple idea in concept. This address identifies the start of the actual network and used to identify a network's existence, so this is the network that sits at the start. You'll very rarely see this .0 address in use by a device because it belongs to the actual network. So for example, a device with the IP address of 192.168.1.100 will be on a network identified by 192.168.1.0 because that belongs to the network. This can be split up a little bit further, but just know that generally that 0 is going to be what identifies the network itself. Let's talk about the host address. An IP address here that is used to identify a device on a subnet, so this is just something that belongs to your device. So for example, a device will have the network address of 192.168.1.10, so this could be a device address with the network address still being this .0 up here. And you can see another example here, where just that last octet is actually changing. Default gateway. The default gateway address is a special address assigned to a device that is capable of sending information to another network. So this is going to be a router. This is essentially how everything needs to go out. Think of if you are in a building that has one way out. That is your default gateway because that's how you need to exit the building or enter it. Any data that needs to go to a device on that isn't on the same network will have to go through this default gateway. These devices can use host addresses, but usually use either the first or the last host address in a network. It's very common to see this be .1. I believe I mentioned that either in the previous video or earlier in this room, where this .1 is often enough going to be a router, or the .254 could be a router as well. Now, in small networks such as at home, you will be on one subnet as there is an unlikely chance that you need more than 254 devices connected at one time. However, places such as businesses and offices will have much more of these devices, so you have PCs, printers, cameras, sensors, and so on and so forth, and that's where you really need to have subnetting come into play. Subnetting provides a range of benefits, including efficiency, security, and full control of how the network is actually split up. We'll come on to explore exactly how subnetting provides these benefits at a later date. However, for now, all we need to understand is the security element to it, because we're focused on becoming security professionals. Let's take the typical cafe on the street. This cafe will have 2 networks, one for employees, cash registers, and other devices for the facility. Hopefully this is on its own network because of PCI. I won't go too far into that. Generally speaking, your cash registers need to be on their own network. And then one for the general public. And hopefully there is no way that these can communicate, because that's where you start having bad things. Subnetting allows you to separate these 2 use cases from each other, whilst having the benefits of a connection to a larger network such as the internet. So know that subnetting, generally speaking, is just how we can separate things off. That's really the big idea out of this section. What is the technical term for dividing up a network into smaller pieces? That is going to be subnetting. How many bits are there in the subnet mask? That should be 32. What is the range of a section octet of a subnet mask? That should be 0 to 255. What address is used to identify the start of a network? Network, that would be the network address. What address is used to identify devices within a network? That'll be the host address. What is the name used to identify the device responsible for sending data to and from another network? That is going to be your gateway. That should be your default gateway here. And there we go. Let's move into task 3, the ARP protocol. Recalling from our previous task that device Devices can have different or two identifiers, a MAC address and an IP address. The ARP protocol, or Address Resolution Protocol for short, is the technology responsible for allowing devices to identify themselves on a network. Simply, the ARP protocol allows a device to associate its MAC address with an IP address on the network. Each device on a network will keep a log of the MAC addresses associated with other devices. So think of it this way. Again, your IP address, that can change. You can swap houses with your neighbor, you can do whatever you want with that, but your MAC address is in theory globally unique. So you probably won't have the same MAC address as your neighbor, and that's something that can be used to identify you uniquely. So even if you move, you still have that MAC address. When devices wish to communicate with another, they will send a broadcast to the entire network searching for the specific device. Devices can use their ARP protocol to find the MAC address and therefore the physical identifier of a device for communication. Think of it this way. Yell out into a crowd and you say, I need the person with this specific MAC address. That person responds, hopefully, if they're not spoofing their MAC address. That's what ARP is doing. It's very simple, and it's just a way of trying to find that unique identifier. How does ARP work? Each device within a network has a ledger to store information on, which is called a cache. That is specifically the ARP cache. In the context of the ARP protocol, this cache stores the identifiers of other devices in the network. So once you've done that yelling out in the crowd to figure out who has what MAC address, you can check your cache because you've already done it before. Why do it multiple times when you know you're going to be sending a lot of data to and from that device? And that saves on network traffic because, again, remember, we only have so much data that we can send at once. We want to keep that as limited as we can just because we want to have bandwidth for other things. In order to map these two identifiers together, the IP address and the MAC address, the ARP protocol sends two types of messages. We have an ARP request, which is that yelling out into the crowd, and then the ARP reply, which is the person in the crowd yelling back that, hey, I have that. When an ARP request is sent, a message is broadcasted to every other device found on a network by the device that has it in theory, asking whether or not the device's MAC address matches the requested IP address. If the device does not have the requested IP address, an ARP reply is returned to the initial device to acknowledge this. The initial device will now remember this and store it within its cache. So again, we yell out and we say, hey, do you have this MAC address? Or hi, MAC address, do you have this IP address? And it'll reply back and confirm it. And then we have that cached. What does ARP stand for? That is going to be just up here at the top, and that is going to be Address Resolution Protocol. And again, that's just so that we can match IP addresses or MAC addresses up with IP addresses, and then there's reverse ARP, which does the opposite, where we can match an IP address with a MAC address. There we go. What category of ARP packet asks a device whether or not it has a specific IP address? That should be a request, as we're asking it. What address is used as a physical identifier for a device on a network? That is going to be a MAC address. And then what address is used as a logical identifier for a device on a network? That is going to be the IP address, because this is just a logical one. This can change. Let's move into task 4, the DHCP protocol.
Zero's hijacked is now following.
IP addresses can be assigned either manually by entering them physically into a device, or automatically and most commonly by using the DHCP, Dynamic Host Configuration Protocol server. You do not need to know what this shortens to. That's just a fun little tidbit. You'll call this DHCP every single time. When a device connects to a network, if it has not already been manually assigned to an IP address, it sends out a request, a DHCP discover, to see if there are any DHCP servers on the network. So it says, hey, I don't have an address. Is there a server out there that can give me one? And you can see the problem with having multiple DHCP servers, because they might both reply, and it might have two IP addresses that are incorrect. The DHCP server replies back with an IP address the device could use, so a DHCP offer. The device then sends a reply confirming it wants the offered IP address, the DHCP request, so it says, hey, I like what you offered, I want to actually formally request that one. And then, lastly, the DHCP server sends a reply acknowledging that this has been completed, and the device can start using the IP address. So it'll send back an acknowledgement, and we can see that broken down here, where we have, hey, I just joined this network, who can give me an IP address? The server itself is going to say, sure, let me go ahead and give you this one. Does that work for you? Yes, that works. I would like to formally request that one. And then it acknowledges it, and usually you have a default time span of 24 hours for that. Let's move into the actual questions here. What type of DHCP packet is used by a device to retrieve an IP address? That is going to be a DHCP discover. What type of DHCP packet does a device send once it has been offered an IP address by the DHCP server? That is going to be DHCP request, because we've already been offered it. We want to say, hey, this is my formal acceptance of it. I do want this address that you've given me. Finally, what is the last DHCP packet that is sent from a device, to a device rather, from the DHCP server? That is going to be our acknowledgement that says, the server says, hey, I see that you're requesting this, I'm acknowledging that request, and I'm going to formally accept it. And that will be the DHCP acknowledgement. Let's move into task 5, request, and I'm going to formally accept it. And that will be the DHCP acknowledgement. Let's move into task 5, continuing your learning with the OSI model. Continue your learning by joining the OSI model room. Highly recommend doing that right after this. If you have any questions, we'll go ahead and mark this as complete. If you have any questions, as always, I will have the Try Hack Me Discord and subreddit linked in the video description below. But otherwise, until next time, happy hacking. Hey everyone, welcome back to another video here on Try Hack Me. I'm John, and today we'll be taking a look at the room OSI model. Learn about the fundamental networking framework that determines the various stages in which data is handled across a network. The OSI model in general, and we'll go into this. In just a moment, is a network that can be used for troubleshooting and sort of breaking down what actually happens on the cables, and furthermore on the actual computer itself when it's trying to talk across these networks. That being said, let's go ahead and dive right into task 1. What is the OSI model? The OSI model, or Open Systems Interconnection Model, is an absolute fundamental model used in networking. This critical model provides a framework dictating how all network devices will send, receive, and interpret data. One of the main benefits of the OSI model is that devices can have different functions and designs on a network while communicating with other devices. So it doesn't matter what the device is, as long as it obeys this model, it still works, and it can still send and receive data across this network. Data sent across a network that follows the uniformity of the OSI model model used in networking. This critical model provides a framework dictating how all network devices will send, receive, and interpret data. One of the main benefits of the OSI model is that devices can have different functions and designs on a network while communicating with other devices. So it doesn't matter what the device is, as long as it obeys this model, it still works, and it can still send and receive data across this network. Data sent across a network that follows the uniformity of the OSI model can be understood by other devices. The OSI model consists of 7 layers that are illustrated in the diagram below. Each layer has a different set of responsibilities and is arranged from layer 7 to layer 1. At every individual layer that data travels through, specific processes take place, and pieces of information are added to this data, which is what we'll come to discuss in the upcoming tasks within this room. However, for now, we only need to understand that this process is called encapsulation and what the OSI model diagram, or it looks like in the diagram below. And here you can see the 7 layers. We have physical, data link, network, transport, session, presentation, and application. Let's go ahead and answer the questions below. What does the OSI in OSI model stand for? That is Open Systems Interconnect. It might be interconnection. There we go. How many layers in digits does the OSI model have? That will be 7 layers, and we can see them above. What is the key term for when pieces of information get added to the data? That is encapsulation. Let's go ahead and move into task 2, layer 7, application. Physical. This layer is one of the easiest layers. layers to grasp. Put simply, this layer references the physical components of the hardware used in networking and is the lowest layer that you will find. Devices use electrical signals to transfer data between each other in a binary numbering system, so ones and zeros. One quick note, there is an ongoing networking joke that layer 0 exists, and it is the human layer, so if you have a layer 0 problem, it's the human that's involved. So if you ever see that come up, that's what that's referencing. For example, Ethernet cables connecting devices, such as the diagram below, so this would be part of the physical layer. Let's dive into the questions. What is the name of this layer? It is the physical layer. What is the name of the numbering system that is both zeros and ones? That is binary. The data link layer focuses on the physical addressing of the transmission. It receives a packet from the network layer, including the IP address for the remote computer, and adds in the physical MAC address of the receiving endpoint. Inside every network-enabled computer is a network interface card, or NIC, which comes with a unique MAC address to identify it. We talked about this in the previous room. MAC addresses are sent by the manufacturer and literally burnt into their card, and they can't be changed, although they can be spoofed in this case. When information is sent across a network, it's actually the physical address that is used to identify where exactly to send the information. Additionally, it's the job of the data link layer to present the data in a format suitable for transmission. What is the name of this layer? It is the data link layer. There we go. What is the name of the piece of hardware that all network devices come with? That is going to be a network interface card, or NIC. Perfect. Let's go ahead and move into task 8, layer 1, physical. Logic of routing and reassembly. Of data takes place, from these small chunks to a larger chunk. Firstly, routing simply determines where the most optimal path in which these chunks of data should be sent. So maybe we have multiple routes to our destination. Routing is going to determine which one is going to be the most ideal, or typically the fastest. While some protocols at this layer determine exactly what is optimal, or what is the optimal path rather, that data should take to reach a device, we should only know about their existence at this stage of the networking module. Briefly, these protocols include OSPF, or Open Shortest Path First, RIP, and RIP rather, a routing information protocol. RIP is really common to see. Don't worry about this too much. You can do different forms of attacks based on this, but we won't worry about that at this point. Just know that they exist. The factors that decide what route is taken is decided by the following. So what path is the shortest? So for example, has the least amount of devices that the packet needs to travel across? What path is the most reliable? So what have packets been lost on that path before? And then last, which path has the faster physical connection? So for example, if one device is using a copper connection, which will be slower than a fiber connection. So it's going to take these factors into consideration when determining how it's going to actually send things across. At this layer, everything is dealt with via IP addresses such as 192.168.1.100. Devices such as routers capable of delivering packets using IP addresses are known as layer 3 devices because they're compatible at working at the layer 3 of the OSI model rather. So again, routers are going to be the big one here that live in this layer because that's where you have IP addresses taking place. What is the name of this layer? It is going to be the network layer. Will packets take the most optimal route across the network? Hopefully. What does the acronym OSPF stand for? We're going to go and copy that up here. Open shortest path first, which is fairly straightforward. What does the acronym RIP stand for? That is the Routing Information Protocol, and we can copy that again. What type of addresses are dealt with at this layer? That is going to be IP addresses. This is where logical networking takes place. And make sure you have plural on that. Let's move into task 7, layer 2, data link. The data link layer focuses. Layer 4 of the Layer 4 of the OSI model plays a vital part in transmitting data across a network, and can be a little difficult to grasp. When data is sent between devices, it follows one of the two different protocols that are decided based upon several factors. So we have TCP and UDP. Let's first begin with TCP. The Transmission Control Protocol, otherwise known as TCP, is a protocol that it's meant for reliability in transport, and we'll get into that in just a moment. Potentially hinted by the name, this protocol is designed with reliability and guarantee in mind. This protocol reserves a constant connection between the two devices for the amount of time it takes for the data to be sent and received. Not only this, but TCP incorporates error checking into its design. Error checking is how TCP can guarantee that data sent from the small chunks in the session of layer 5 has been received and reassembled in the same order, so we have accuracy of that data being transmitted. Let's summarize the advantages and disadvantages of TCP in the table below. So, some advantages. Again, this guarantees the accuracy of the data because we're checking it once it's received on the other side. It's capable of synchronizing two devices to prevent each other from being flooded with data, and it performs a lot more processes for reliability. Disadvantages, this requires a reliable connection between the two devices. If one small chunk of data is not received, then the entire chunk of data cannot be used because we have to resend that packet. Another slow connection can bottleneck another device, as the connection will be reserved on the receiving computer the whole time. It has to be active. TCP is significantly slower than UDP because more work has to be done by the devices using this protocol because we're checking things and maintaining that connection. TCP is used for situations such as file sharing, internet browsing, or sending an email. This usage is because these services require the data to be accurate and complete, and there's really no good in receiving half of a file. In the diagram below, we can see how a picture of a dog is broken up into smaller pieces of data known as packets from the web server, where the computer reconstructs the picture of the dog in the correct order. So it's broken up into these packets. In theory, these would be a lot smaller than this, and we can see how it's finally reconstructed at the endpoint. Now let's move on to User Datagram Protocol, or UDP for short. This protocol is not nearly as advanced as its brother, the TCP protocol. It doesn't boast the many features offered by TCP, such as error checking and reliability. In fact, any data that gets sent via UDP is sent to the computer whether it gets there or not. There is no synchronization between the two devices or guarantee, just hope for the best and fingers crossed. While this sounds disadvantageous, it does have its merits, which we'll lay out on the table below. So it's much faster than TCP. A lot of this is kind of the inverse of what we saw with TCP, so a lot faster. It leaves the application layer user software to decide if there's any control over how the packets are actually sent. UDP doesn't really care. It's up to the actual user software to kind of decide that from there. And UDP doesn't reserve a continuous connection, so it doesn't bottleneck the device there. Disadvantages, it doesn't really care if the data is received. It's going to send it anyways, and it's going to keep on going. It is quite flexible to software developers in this sense, which is good and bad. It depends on how it's implemented. The biggest thing to think of with UDP is something like Skype or video calls, which UDP is perfect for, because you're sending a lot of data, and maybe you hit a little small hiccup that the video connection doesn't quite, it might make you sound like a robot for a little bit, or things like that. But you just want it to keep moving on, because you don't want to see something from 5 minutes in the past suddenly flash on the screen. That might be terrifying. But in this case, you want it to keep moving, and that's the idea with UDP. You want that data stream to keep continuing. And with it not reserving that connection, this means that on unstable connections, it might be a bad experience. And you've probably seen this before when Skype was first coming out, that it wasn't always great. It wasn't always a great connection. And even then, sometimes you can see that with streaming services like Netflix or other things, where sometimes you just hit a rough patch in the internet that a lot of people are on, and all of a sudden your connection just doesn't really work that well. Using the same example as before, we can now see that only packets 1 and 3 have been received by the computer, and you end up with this horribly disfigured dog. And you can see how UDP can sometimes not always be the best choice. UDP is useful in situations where there are small pieces of data being sent, and we mentioned here that video streaming are really large files where it's okay, maybe if you're watching a video on YouTube, that it's okay if part of the video is pixelated because it'll pick itself up here in just a little bit. That happens, and that's where UDP is really useful. Let's go ahead and dive into the questions. What is the name of this layer? Gotta double check what layer we're on. Transport, there we go. What does TCP stand for? That is Transmission Control Protocol. What does UDP stand for? That should be User Datagram Protocol, if I have that typed correctly. What protocol guarantees the accuracy of data? That will be TCP. What protocol doesn't care if the data is received or not by the other device? That will be UDP, because we're not actually checking it when it's received. What protocol would an application such as an email client use? That hopefully is TCP. What protocol would an application that downloads files use? That would be hopefully TCP as well, if you want to guarantee that you're receiving all of the data and it's correct. And what protocol would an application that streams video use? Like the UDP. All right, let's go ahead and move on to task 6, Layer 3 Network. 5. Session. Once data has been correctly translated or formatted from the presentation layer, the session layer will begin to create a connection to the other computer that the data is destined for. When a connection is established, a session is created. Whilst this connection is active, so is the session. The session layer, layer 5, synchronizes the two computers to ensure that they are on the same page before data is sent and received. Once these checks are in place, the session layer will begin to divide up the data sent into smaller chunks of data and begin to send these chunks, packets, one at a time. This dividing up is beneficial because if the connection is lost, only the packets that weren't yet sent/received will have to be sent again. Not the entire piece of data, so think of it as loading a save file in a video game. What is worthy of noting is that these sessions are unique, meaning that the data cannot travel over different sessions, but in fact only across each session that it's specifically destined for. Let's move into the questions. What is the name of this layer? It is the session layer. What is the technical term for when a connection is successfully established? It should be, let's see, I'm guessing created. Let's go ahead, I'll pause this for just a moment and double check my notes. All right, there we go. So we're specifically looking for the term session. So that's saying that the connection has been established and we've created a session. What is the technical term for small chunks of data? That is packets. And there we go. Let's move into task 4, layer 4, or task 5 rather, layer 4, transport. Layer 4 of the OSI model plays a vital part in transmitting data across a network. Layer 6 of the OSI model is the layer in which standardization starts to take place. Because software developers can develop any software, such as an email client, differently, the data still needs to be handled in the same way, no matter how the software works. This layer acts as a translator for data to and from the application layer, layer 7. The receiving computer will also understand the data sent to the computer in one format destined for another format. So, for example, when you send an email, the other user may have another email client than what you have, but the content of the email will still need to display the same. Security features such as data encryption, like HTTPS when visiting a secure site, occur at this layer. What is the name of this layer? That is the presentation layer. What is the main purpose that this layer has? That is standardization, if I can spell it correctly. Not even close. Wow. Let's copy that, and we're going to paste instead of me trying to spell things. Or we're looking for translator, rather. Give me a moment. And we're just going to ignore that I can't spell. And it got even worse. Wow, we are getting worse by the second. Okay. Perfect. Let's move on to task 4, layer 5, session. Once data has been correctly translated or formatted, layer 7 application. The application layer of the OSI model is the layer that you will be most familiar with. This familiarity is because the application layer is the layer in which protocols and rules are in place to determine how the user should interact with data sent or received. Everyday applications such as email clients, browsers, or file server browsing software such as FileZilla provide a friendly graphical user interface, or GUI, for users to interact with data sent or received. Other protocols include DNS, domain name system, which is how website addresses are translated into IP addresses. And you can see just an example of interfacing with an FTP server, file transfer protocol. What is the name of this layer? This is the application layer. What is the technical term that is given to the name of software that users interact with? That is a graphical user interface. And there we go. Let's move on to task 3, layer 6, presentation.
Anti 1001 is now following.